Okay. So here's the problem. Want to sketch an exponential curve through these points. And then we want to find the equation of the exponential function. Form is y equals ab to the x. And people have done the homework, know that you're going to get two simultaneous equations. You're going to solve them for a and b. Okay, it's fairly easy. And then the question is, what is the growth rate and the growth factor? Okay. So instead of your a and b numbers, I'll just use a couple of typical numbers here. So we're going to say this is maybe 6, 8, and this is maybe 17. Well, it's just random numbers pretty much. The only thing is A, B, C, D, E, and F and G are in increasing order. Okay. So sketch an exponential curve. Well, exponential curve starts real close to the x-axis. So if you want to draw a good exponential curve, and everybody pretty much did. I think there's at least one of them that went through the x-axis, and don't do that anymore. Okay, because your asymptote would then be below the x-axis. And you've got a horizontal asymptote for reasons that I think you understand. But we come along here till we go through here, and then we come on up, right? So I'm going to say, okay, let's do something like this. That's better than I expected. Okay. Must be doing better than usual today. Okay, so I actually kind of hit the 2 points, and it kind of looks like an exponential curve. Okay, now we want to find the equation of this exponential function. Okay, so one form of the equation is y equals ab to the x. Well, the point 6, 8 implies that a equals ab to the 6th power. And the point 17, 12 implies that 12 equals a b to the 17th power. Okay. Now there are a couple of ways to solve this system of equations. So I'm going to ask everybody, or somebody at least, to tell me how you would go about solving it, or how you did go about solving it. Okay, again, I'm not sure what I recorded and what I did. But here are the 2 points that we're looking at. Everybody have their AB and ED numbers here. We sketched an exponential curve asymptotic and negative x-axis through these points. And that looks like a pretty good curve. I think I kind of lucked out on that. Okay. Find the equation. And I committed myself to the idea that's a pretty good exponential curve. Now the whole universe can check me on that, okay? And make a fool out of me if they wish. At some level, it's not going to be accurate. Okay, whether it's a decent degree of accuracy or not, yeah, it's worth trying to make it accurate, just to get your head into the situation. I'll try to do better than I can, which is not that hard to do. Okay, now we find the equation of the exponential function. Well, it's y equals ab to the x. Okay, there's the form. I gave you the form, but you should know that's a general form of the exponential function. That comes right out of your homework. Am I right about that? Okay. That's a general function that the MyLab problems pretty much give you. So, in point 6.8, well, that means that when x equals 6, y equals 8. So we get 8 equals ab to the 6th. And 17, 12, well, x is 17, so there it is. Y is 12, so there it is, right? How do we solve it? Okay, one way, it's maybe not the most convenient way, but it works. Okay, there's another way that I'll show you, and you can use whichever you prefer. Either way, you're going to get a solution, and either way, it's a valid way to do it. So solve the first equation. Let's call this equation 1. Call this equation 2. I don't have to do the algebra for you. Just going to divide both sides by b to the 6th. And it's very obvious that you're going to get a equals 8 over b to the 6th. Then you plug this into the second equation. You plug into the second equation and you get 12 equals a over b to the 6th times b to the 17th. Okay. So a equals it's 8 over b to the 6th, not a over b to the 6th. And I should point out here that we've eliminated a. A is no longer appearing in the equation we get. Okay, so what do we get here? Well, b to the 17th over b to the 6th is b to the 11th. And then we're going to divide both sides by 8. So we're going to get pretty quickly b to the 7th. I've got to stop this thing of writing down the last word that I said, write down what I should be writing down. We get b to the 11th equals 12 over 8. Okay. That's pretty good. Let's make sure we understand. B to the 17th over b to the 6th. You got 17 b's multiplied out on the numerator, 6 of them in the denominator. You group 6 of them in the numerator with 6 in the denominator, and that gives you a 1, and then you have 11 left over. Okay. Now, how do you solve this equation? Well, this is basic algebra. If you're a little fuzzy in the basic algebra, I want to review your rules for exponents, okay? But this says that b to the 11th to the 1/11th equals 12/8 to the 1/11th. Okay, you can call that the 11th root also. But I'm going to do it with exponents because actually you have a nth root function on your calculator. You could use it. Okay. I'm going to do it this way. B to the 11th to the 1/11th is B to the 11 times 1/11. Because when you raise to a power, you multiply the powers. And this equals, well, the 1/11th power of 12/8. Now, what's the 1/11th power of 12/8? I can fool around and try to estimate that. The 1/12th power would be the cube of the 1/4 power. I didn't say that right, but and the 1/4 power of 1.5, square root of 1.5, so 1.03 maybe. Okay. Now you can test that on your calculator. I'm not real confident in that, but it's probably somewhere in that range. And of course, 11 times 1/11th is b to the 1 equals approximately 1.03. And of course, that's b approximately equals 1.03. Then what's a? Well, A is approximately A over B to the sixth, which would be approximately, because, well, it equals 8 over B to the sixth. That's approximately equal to 8 divided by 1.03 to the sixth. Now kind of cheat, the sixth power of 12/8 to the 1/11th is the 6/11th power of 12/8. And that's a little more than the 1/2 power of 12/8. The 1/2 power of 12/8 is a little over 1.2. So I'm going to say that's about I'm just going to make a wild guess. Okay, it's not that wild. You say maybe that's about 1.27. Now you can check the numbers because these are just done in my head. And they could be wildly incorrect. But what I'm saying then is that my function should be y equals AB to the x. You make that out? I got too close to the edge of the board. Really should practice doing better with that. I think it's genetic. Okay. I want to leave myself room to do some projections and stuff. Before we get that out. Okay. Okay, so we've got a solution. An approximate solution that I think might work. I can now make some estimates. Now, first of all, okay. What are the growth factor and the growth rate? You haven't got those on your paper. You're checking my numbers. Go ahead, but if you don't have the growth rate and growth factor on your paper, write them down and circle them so I can see them quickly, and I'll walk around and see if we're in good shape with that. Okay, now the growth factor is just your base. It's 1.03. Growth rate is the 0.03 or 3%. It's like, as an example, you've got an investment at a certain percent rate. Okay. After 6 years, you're up to $8. And you're feeling pretty rich, but you're going to keep it in. Okay, maybe this 8 is in thousands of dollars. Okay. So maybe after 6 years, you have $8,000. This is saying that whatever this thing is, after 17 years, you've got $12,000, right? Now that means in 11 years, you went from $8,000 to $12,000. Okay. And that three looks a little low, it's probably close to 1.0, but that's okay. Then the 1.03 is your growth factor. That means every year you can multiply what you have by 1.03. Okay, and again, probably closer to 1.04 when I did my estimate. I wasn't thinking in terms of doubling times and so forth. Okay, so 1.04 would have been better here. That would have affected our number here. So this model isn't really great for this curve. But what you get if you do it accurately with a calculator will be a very good approximation. Doesn't really matter. This would say then, if every year you multiply how much money you have by 1.03, well, 1.03 is 3% more than 1, right? Okay. So if you multiply by 1.03, you're increasing your amount by 3%. So let's make sense out of this. $1.03 is 3% more than 1. So anything you multiply by 1.03 ends up increasing by 3%. Okay. Every time X increases by 1, you multiply by 1.03 another time. So if Y is the value of an investment, and it's worth 8,000, I'd say in year 6, you want to say at a specific time in year 6, but I didn't want to write all that out. Okay, but let's say on January 1st of year 6, it's worth $8,000. Then it'd be worth 1.03 times $8,000 in year 7. Now let's look at this, okay? Okay, in year 6, it's worth $8,000. In year 7, you multiply that by 1.03 times 8,000. Okay, it'd be $8,240, but we're not worried about the numbers right now. Worried about what's happening with this growth factor. This is your growth factor. It's what you multiply your value by to get your value 1 unit of time later. In this case, 1 year later. Then in year 8, we multiply this by 1.03. Okay. In year 9, we multiply by 1.03 again. So here we've got 1.03 times 8,000. Here's our 1.03 times 8,000. We multiply that by 1.03. Then in year 9, we multiply 1.03 times this. So let's say this is what I've underlined in purple. Here it is. So every year we multiply by 1.03. Okay, not unexpectedly, I made a mental error here. 1.03 to the 6th power should be 1.27. I should be dividing 8 by 1.27, which is the same as taking 4/5 of 8, which would be 32 over 5, which would be 6 point. Right in the middle, saying it. My brain got distracted. Probably by cosmic rays or something. Let me go. Okay, so it would be like
I've got it right here.
don't tell me. It's no fun. Help me in a minute so I can see how bad I am. Okay. Okay, so again, 1.03 to the 6 would be about 1.27. It's about 1 1/4. If you divide by that, that's 5/4. You take 4/5. Yeah, 4/5 of 8 be 24. 4/5 of 8 be 32 over 8, which would be 3 point. That would be 4. So I think that's not. No. Doggone it. Once more. And if I don't get it this time, you just get to tell me. Yeah, you divide by 5, it'd be 6.4. Okay, so what should it have been?
6.299.
Okay, we'll say I get 6.4. So your calculator isn't that far off if you think it's 6.29, okay? So you probably don't need to get the thing serviced just yet. Thank you. Okay, so I'm gonna go with 6.4 here, and then I'm gonna fix my 1.27. 6.4s. There's one. I think this is the only other one I've got on the board. I got so busy approximating 1.03 to the 6th that I didn't think to divide it into the 8. Just another example of what you shouldn't be doing. You should be doing it more carefully and more completely. Of course, writing it out helps. Okay. And let me also stress, and I've got people in some classes, not this one, who are trying to learn their subject matter by watching videos, just watching and reading. Okay? It doesn't work for most people. Yeah, if your brain works a certain way, it might. Writing things out is the way to go. And when you're doing open math, writing things out coherently, as I keep stressing, is really important for locking in the ideas. I think I use this in a different class. I'm repeating myself. I'm trying to learn some more advanced quantum mechanics, okay? But I'm intentionally trying to learn it without writing anything out. Okay? And I keep forgetting what I knew 2 weeks ago because I haven't written it out and haven't reinforced it. So I got to go back and keep remembering until I remember it. Okay? It's taken me a long time. It'd be much quicker and more effective if I was writing it out, and even more so if I was teaching it. Not that anybody in their right mind would have me teaching an advanced quantum mechanics course, okay? Yeah, somebody who's been working in the field for years is who ought to be teaching that course, okay? So I I never presume, especially at my age, to learn it well enough. Teach it. Might not even be smart enough to learn it well enough to teach it, even in my prime, because it's really tough stuff. Okay. But I'm kind of doing that just to put myself in the place of a student, also just to, check out how my brain's working. And it turns out not all that well, but it's okay. Okay. My point is, make sure you write things out coherently, and most of you are pretty good at doing that. The more you do that, I think the better you're going to learn, although you can take it to ridiculous extent. Okay, back to what we're doing now. You've got the correct number in front here, and thank you for correcting me on that. Here we've got year and value. You see that every year we multiply by 1.03. So that what we get in year 10, well, I'm getting tired of writing out all these 1.03s. How many 1.03s am I going to have here? Show me with your fingers. Year 9, how many 1.03s do I have? Yeah, I have 3. Going to multiply by another one. How many is that going to be? Very good. Okay, 4. Well, what do I mean by multiplying 1 or 1.03? So that's 1.03 to the 4. And then in year N, okay, so in year 20, how many 1.03s am I going to have? I'm going to have 10 more, right? Okay. Turns out in year N, it's going to be 10. It's going to turn out to be N minus 6. Okay. The 4 here is because you've done this 4 times, right? And you've done it 4 times because you're doing it since year 6. So in year N, you'll have done it N minus 6 times. Well, that's the meaning of the 1.03. My point is every year you multiply by 1.03. Now, if we started at year 0, in year 6, the value is 8,000. Well, if we go back to year 0, it turns out we're going to have $8,000 divided by 1.03 to the 6th. Not going to go into the details of that, but see what you get if you divide 8,000 by 1.03 to the 6th. You've got your calculator. you get about 6,400, right?
Yeah.
Okay,
Yeah, 66.
approximately 6,400. Well, that, it's 8,000 corresponds to 8. 6,400 would correspond to 6.4 thousands, right? So what we would have here is 6.4. Now let's, I thought I had a pretty good exponential function there. It's not all that great. However, these points aren't really to scale. So it doesn't quite look right. If the points are to scale, it hopefully would have drawn a better exponential function. If this is 8, this is a lot less than 6.4, right? But of course, if this is 8, then 12 is only up about here. So the curve would be a lot shallower. Okay, well, all that's kind of getting away from the point. I'm not sure it was a really great idea to do this, but I do want you to see the idea that 1.03 is what you multiply by every year. That's the bottom line. Don't worry about the rest of it. That's why we call that the growth factor. Okay. And then what happens if you multiply 8,000 by 1.03? This is 3% more than 8,000, right? So this is this is 3% more than this. Can't get my arrows to go right. But and then this is 3% more than this is 3% more than this, and so forth. That's how compound interest works. That's how exponential growth works. If it's a population, okay, if it's a population of fish introduced into a pond and the pond has plenty of food, there's plenty of room for all the fish, then the fish are going to tend to increase maybe by 3% every week or every month, depending on what kind of fish you have, okay? Because the more fish you have, the more new fish you're going to have. Fish reproduce at whatever rate their biology dictates, if they have unlimited food and no competition. So you might have a 3% increase in the fish population, at least till the pond starts getting crowded and all the nutrients get used up and predators move in, okay? So that's the way populations work, it's exponential. Up to the point where things get competitive and then it tends to level off. It's what we call carrying capacity. You see that in some of the problems in the pre-calculus at least, maybe not in this support course. Many other things. I mean, a whole lot of other things. Okay. I just had a good example in mind. There are numerous examples. What was I thinking of? You got populations on. We used the example of radioactivity. Okay. Radioactive substance changes at a constant rate, but it goes down by a certain percent every time period. Okay. Here's an example. Okay. Now, you notice I got these braces here. I got a little carpal tunnel trying to cure it. Not sure it's getting any better. Not sure it's getting any worse, but okay. I got an owie. Okay. This thing is kind of chafing here, kind of breaking the skin. Okay. It's a liquid bandage. Now, every time I open this liquid bandage, let me just Take this off for a minute. To demonstrate this is a real process. Every time I open this liquid bandage, try to slop some of it on that spot. The stuff keeps getting thicker. Okay. That might or might not be a good thing. It might be more protective. Why does it keep getting thicker? It keeps getting thicker because every time I take this cap off, I'm exposing it to fresh air. Then I seal it up and the fresh air interacts with chemicals in this thing. It makes it a little thicker. Because of course, it's supposed to thicken when it gets air. Now there's enough of it in the container that at the beginning and for quite a long time, it doesn't show that it's getting thicker. Okay. But it is imperceptibly along the curve like this. At least theoretically. The thicker it gets, the less of the chemical there is to interact with the air. Okay. Well, actually, probably shouldn't have said that. Okay, every time I apply it, there's less chemical in there. Okay, there's less of the liquid. Okay. And the same amount of air, actually a little more air gets in as the liquid level goes down. Okay, so it's not going to be a perfect exponential, but you get the idea that if there's less of it being exposed to more air, it's going to get thicker faster. Okay, because a bigger percentage of it will interact with that air. So it's a case where the more you've got, the faster it changes. Or the less you've got, the faster it changes. Okay, as time goes on, it changes faster and faster, kind of along an exponential curve. Now I could put conditions on this, keep the amount of air that goes in constant, figure out just how we're going to measure thickness. And we probably wouldn't have a perfectly exponential curve. But our starting point would be, yeah, this is kind of how we expect the thickness to go. Not much change for quite a while, and then starts changing a little faster, then all of a sudden, it's thick. Okay. It's getting thicker, faster and faster. And it's down to the point where I don't think it's going to last too much longer. That's okay, because that whole bottle only costs about $1.50. It's lasted me a couple of months. Okay, it's not going to severely affect the worldwide economy. And if I've got to throw away a quarter's worth to get the benefit, keep my hand from developing gangrene and having to be amputated or whatever happens, this goes on. Okay, well, extrapolating exponentially to what might happen. Okay. So I'm going to stop talking about this now. These are a couple of important points. There's another important thing, though, about an exponential function, which is its doubling time. Okay. In order to get a handle on doubling time, remember your basic exponential function doubles every time x increases by 1. Okay. Your basic exponential function is 2 to the x. What's 2 to the 0? 1. Right? Now increase x by 1 from 0 to 1. What's 2 to the 1? It's 2. It just doubled, didn't it? Now go up to x equals 2. What happens? 2 to the second. That's 4. It doubled again. It was 1, then it was 2, then it was 4. Each time it doubled. And if you start over at x equals -2, it was 1/4. Then 1/2, which is a double of 1/4. Then 1, which is a double of 1/2, and so forth. So the basic exponential function doubles with a period of 1. Or the doubling time is 1. One doesn't really want to say a period, it's not a repeating function. Okay. It's a word for that. So it coming into my head, I should know it all over the place. the whole thing is, and all this, yeah, pretty much, okay. So in order to start getting a handle on doubling time, we need to talk about logarithms. Now let's go back. Doubling time of this function is x changed from 6 to 17. That was a change of 11. We went from 8 to 12, even though the scale is wrong. Okay. So if we were to double, what would we have to get? We'd have to get 16, right? Y is 8. Okay, $1,000. We're going to double $8,000. That's $16,000. If I talk about money, you can calculate it instantly. Okay, because you used to think about money. It is important. So the doubling time would be whatever time it takes us to get up to 16. Okay, from 8 to 16. Then, in the same doubling time, it would go from 16,000 to 32,000. It would double again. So in this case, doubling time is something on the order of 22 years, I guess. Say 20 years. Okay, I think that's a little short, but let's say this thing doubles in 20 years. So you got $8,000 now when you're 20 years old. Okay. By the time you're 40, it's going to be worth $16,000. Now, the question of inflation eat most of that up or overwhelm it. Yeah, that's a different question, but inflation tends to run exponentially too. So let's just say the numbers. Okay. Assuming that the economy is such that on the long run, the value outpaces inflation. It's not so much true in the last year, but it tends to stay true. Hopefully, we'll continue to do that in your lifetime. So you got a doubling time of 16 years, of 20 years. You double from 8 to 16,000 in 20 years. So by the time you're 40, you got 16,000. Okay, then it doubles again. By the time you're 60, you got 32,000. Quadrupled your money. You probably lived to 80. Okay. By the time you're 80, when you really need it, you got 64,000 when you started with 80. That makes sense. Okay. So, other examples. You can think of fish in a pond, population doubles. First of all, you don't really notice you get more fish. All of a sudden, you're up to your elbows with fish. Okay. Exponential functions behave that way. Okay. Switch gears. Going to talk about logarithms. So, your basic exponential function. There are your values. You know what the graph looks like. The log base 2 function, which we have mentioned in pre-calculus class. I think we might have mentioned it in here. Log base 2 function, it's the inverse of the exponential function. So you just switch the and you have this. But what's the log base 2 up 2 to the x? These are inverse functions. So that the log base 2 of 2 to the x is like an f inverse of f of x, which always has to equal x. So the log base 2 of 2 to the x should equal x. Is it true? Well, pick an x in the table. Which x do you want to use? Show me with your fingers. Not yet. Let's not use 0. 2. Okay. So if x equals 2, then 2 to the x equals 4, right? What's the log base 2 of 4? Over that table, tell me. 2. Okay. Pretty obvious. If x is here, then 2 to the x is here. Then the log of 2 to the x is here, which is this. Okay. So log base 2 to the x equals x is an instance of this because for example, if x equals 2, what's log base 2 of 2 squared? Putting x equals 2 in here, right? That's log base 2 of 4. Go to your log base 2 table, there's 4. Log base 2 of 4 is 2. It's going to be true for any other value. Take any value in this table, plug it in over here, and you're going to get back what you started from. Okay? And say that exactly right. Take any value over here, find y, which is 2 to the x. And then put that into a log function, and you get back to the number you originally started with. Okay. So in general, y equals b to the x is inverse to y equals log base b of x. And it works the other way too. F of f inverse of x is x. That would be this. So here's your two defining characteristics of the log base b function. If you want to do a graph of log base b, like if you want to do log base 1.03, take the 1.03 to the x function, make a table, invert the values in the table, and you get your graph of the log function. You're going to see that in the book. Okay, now, this log thing is very handy. One other really important property of the log before we get into the ones that are a little harder to understand. It's kind of usually the last one people mention, but it's the first one I'm going to mention. Okay. Log base B of X is log of X over log of B is the natural log of X over the natural log of B. Now, by the log log, we mean the log base 10. Because it'd be, log base, it'd be inverse to 10 to the X. You're going to see that in the homework. Okay. It's real easy to raise 10 to integer powers, right? So you kind of understand the log log. The problem with the log log is it gets really, the problem with the log log is it's inverse to the 10 to the X function, and the 10 to the X function blows up really fast. Okay, like 10 to the 6 is over 1 million, whereas 10 to the 1 is just 1. Okay, so it gets really big values. It's kind of hard to graph it accurately. Although there are certainly things you can do. Okay, the natural log of X is log base E, where E is a number between 2 and 3. Now you could graph 2 to the X, and you can make a table and graph 3 to the X, right? So the E to the X function is somewhere between the 2 to the X function and the 3 to the X function, which is somewhat steeper, but still something you can understand. We're going to talk about that, but right now, all you need to know is it's a button on your calculator, and this is a button on your calculator. Okay? So if I ask you to do log base 1.03 of 75, you can punch that into your calculator by doing the log of 75 divided by the log of 1.03. Now we're going to do that in a minute to see what the doubling time of this function ought to be. Okay. We're going to apply these properties. So let's just apply these properties to the question of the doubling time. We have this. I could use that. So this is here and that's there. Yeah, couldn't need to do that. Okay. Okay. We're going to find the doubling time of 6.4 times 1.03 to the X. You're going to write an equation. I want to know the value of X for which 6.4 times 1.03 to the X becomes twice as great. So we're going to find the X that makes this double. Okay. So here's your double of 6.4. I can say a little more, but we're going to just kind of keep it that right now. Okay, what's the first thing you would do to this equation in order to solve it for X? Okay, it should be pretty obvious that we can divide both sides by 6.4. Well, when we do that, the 6.4 divides the 6.4, it leaves us 1.03 to the x. And same thing happens over here, but that leaves us 2, right? Okay. Well, now what in the world are you gonna? Okay, well, I didn't really give you time to ponder. The point is, x is in the exponent here. You can't get to it unless you use this. Okay, so I'm going to say this. I'm going to say the log base 3 of this has to equal log base 1.03 of this equals log base 1.03 of this, right? Now you haven't digested this, but if you look over here, what's the log base b of b to the x? It's x because these are inverse functions. Well, log base 1.03 is inverse to the 1.03 to the x function. So this tells us that x equals log base 1.03 of 2. So once you get used to this property, it becomes a real easy way to get at the x in your exponent, okay? Get at the unknown in your exponent. Unknown isn't always x. How do we do log base 1.03 of 2? Log base b of x is log x over log b. You go to your calculator. Got your calculator handy? This part is really easy. You just punch it in. And it doesn't matter if you use the log log or the ln log. We'll see why later. Okay, so you have a calculator. It's really easy to punch this in. You're going to get something close to 24. When you get a calculator in your hand, try it, or open math to run you through it too. So I think you're going to have no problem with this. Okay, this seems a little strange at the beginning, but it's very easy. If it occurs to you to do it. Okay, you got to recognize that this is an exponential equation. Your variable's up there in an exponent, okay? And you got to isolate it to this form. So you have a b to the x equals whatever, okay? Just like if there's a quadratic equation, you can solve it if you recognize that it's quadratic. Okay, try to solve a quadratic equation using your techniques for linear equation, and everybody tries to do that. You learn pretty soon that that's not going to work. You got to recognize that it's quadratic and apply the quadratic formula. Here, you got to recognize when you see something like this, that it's an exponential function, and you got to get rid of everything in front of the exponential function here, so you have something, a base to power equals something, okay? So you do, now it's a little helpful to see this, okay? So I'm not even going to use X, I'm going to use A. I've got a capital C there, but I look like a capital. The B to the A to C is equivalent to what? Equals to log base B of C equals A. Morning. So. Five to three x minus 7 equals 12. Is that in this form or this form? It's in this form. She say. This. So now your 3x minus 7 is right there on this side where you can just apply your regular rules of algebra. And that equals log of 12 over the log of 5, which is an equation. Log of 12 over log of 5 is just a number that you can evaluate with your calculator. Use the LOG or the LN button. And then you can solve for x. So that with a little manipulation, you add 7 to both sides. So you get a log 12 over log 5 plus 7, which I've got right here. And then divide both sides by 3 to give you the 1/3. And you just punch this into your calculator and you've got your solution for x. Okay. And you're better off to rearrange to this form. Over time, real quickly. Then the equation log 2 of 5x plus 3 equals 4 is equivalent to what? If you use this, your b is 2, the c is your 5x plus 3, and the a is 4. Okay, so you come up to this form. What's your b? It's 2. So you get 2 to the a. What's a? It's the 4. 2 to the 4th equals 5x plus 3. We take the logarithmic form, we change it to exponential form, and it's easy to solve. That's just 2 to the 4th is 16. 5x plus 3 equals 16. It's a really easy equation. Okay, you get 13/5. X is 13/5. You can do that in your head practically. So there are 2 types of equations that you didn't used to know how to solve. You had no clue how to solve this until we introduced logarithms. And no clue how to solve this until we had logarithms. But now we've got logarithms. Now logarithms have additional properties that you're going to want to learn. But this is why we learn the properties of logarithms. And the properties of logarithm are closely related. They're kind of inverse to the properties of exponents. So your assignment for next time will address all that. Okay. So I believe you'll be in pretty good shape with this. This is not a particularly difficult part of a pre-calculus course. Now it can lead into things that are very challenging. Okay, it's actually easier than rational functions for most people. Most people, when they get to this, kind of go, I'm glad we're here now. It's unfamiliar, but it's not that complicated. Okay,